So, okay, so now we're looking at question 3. All right, question 3. Okay. So we're interested in the number and the amount of times in a month that Americans think of bacon. Okay, so this is something people would want to know. So we're looking, so we find n equals 36, x bar equals 18, s squared equals 9.371, and we have alpha equals 0.0 or 0.1. Okay. Okay, so before we even start, we're going to want to find s because that's what we actually want. And the square root, we find s just in the way that we find sigma from the variance, which is sigma squared. And we do that by square rooting it, which turns out to be 3.061. 0.061. Okay, so what we're interested is that someone tells me that they think that the true mean value is 19. Okay? And I say, no way, I don't think that. I think the true value is less than 19. Okay? Okay, so how do we test that? We do exactly a hypothesis test. So the first thing we have to find to do a hypothesis test, we find the test statistic. And this is where you're encountering your first question, which is whether or not we do a z or a t. Okay, a z or a t test. Okay? And the way we figure that out is by looking at the number of samples that we collected, which is 36. And what the CLT tells us, which is the central limit theorem, that tells us that if we have n greater than or equal to 30, then we can use the z. The t approximates the z at n greater than or equal to 30. So we do the z equals x bar minus mu naught, which is this value, what we think our null hypothesis mu value is, divided by s over the square root of n. Okay, and this is 18 minus 19 over 3.061 over square root of 36. And that turns out to be negative 1.96. All right. Okay, so again, this is not a probability. This is a z-statistic that we use to find a probability. Okay, and what we do, that's pretty good looking. So we have starts at 0 because this is a z-statistic, so z is normally distributed with a mean of 0 and a standard deviation of 1. Consider like our z score, basically. So we say, okay, a negative 1.96. We look in our table. We find that this is 0.025. Okay? All right. So that's, okay, so this is our p-value. This is the thing that we want. We want the p-value. Okay, now I'm going to erase all this and kind of explain what a p-value is. Okay, our p-value okay, so this is extremely important. Okay, you're going to get questions on this, about this all the time. So the p-value is the probability of observing the value that you found, which is x bar, or something more extreme than x bar, which is x bar, which is 18 or less than 18. So 18, 17, 16, all the way down to 0, which is not really possible, but not probable. So 18 or less than 18. So the p-value is the probability of getting the value that you found or something more extreme than you found, given that h0 is true. Okay? So what we're finding is the probability of getting what we found, given that the true value is 19, is 0.025, okay? Which means we have a low chance of getting this given this, okay? And that's why when we have a low p-value, we reject h0, because this is basically telling us that there's a lot of evidence to say that this is not true. because we got this value. We found 18 to be the mean of 36 people, okay? And we just kind of think that this is true. So we need a lot of evidence to say that this is probably true. And since we basically have no evidence, very small chance of this happening with this being true, that's why we reject H naught in favor of mu being less than 19. And that's how we, okay, so this is the conclusion. We say we reject because we have a low p-value. Okay? Okay, so we found that. That's all great and dandy. Now notice that 0.025 is greater than 0.01, okay? But it's less than 0.1. Okay, so this relation right here told us we reject H naught because our p-value is less than alpha. Less than alpha. Okay? But in the question I ask you, is it less than 0.01? And it's not. It's greater than 0.01. So if alpha were instead 0.01, we would not be able to reject H naught. We would say there's not enough evidence. But in this case, alpha is just 0.1 and we reject. Okay, so now we know, we don't know for sure, but we have good evidence to tell us that mu is not 19. So let's create a confidence interval, specifically a 90% confidence interval. Okay, so the general form is x bar plus or minus z alpha over 2 times s over the square root of n. Okay, what this means is 18, just plugging it in. Z alpha over 2 is the alpha level that's associated with 0.05 in the tail. So what this is 0.05 in here and 0.05 in here, which is exactly 90% in here. And if you look in your t-table at the infinity values, you get the same thing. So at the bottom row as the infinity values in the t-table, this will give you the exact same thing, which is 1.645 times 3.061 over the square root of 36. Okay, and this turns out to be 17.1607. Okay, and what this says is that we're 90% confident that if we did this a bunch of times, the same setup, did a bunch of times, 90% of the intervals that we found would contain the true value of mu. Okay? 10% wouldn't. 10% we would mess up and not have mu. But 90% of the values would have mu. And what that means is we don't know if mu is in this range, but we're pretty sure. We're 90% confident. And that's the interpretation of the confidence interval. Okay, so does this confidence interval support our conclusion of rejecting? And the way to see that is to say, okay, does my interval contain the mu naught value? Okay, remember h naught, ho, mu equals 19. Okay, and mu naught is 19. Does this interval contain 19? It does not. Okay, so that supports it. That means that like the probable values of mu are in this range. 19 isn't one of those probable values, so we're fine. We can reject. Equally from this as well. Okay. Okay, so that's the end of the question.